When Neil deGrasse Tyson made his unexpected revelation about Neptune, it didn't just ripple through the astronomical community. It shook the very foundations of what many believe to be a well-understood realm of our solar system. Known for his eloquent articulation of complex astrophysical ideas, Tyson took the stage at a packed, globally streamed symposium and delivered a statement that left viewers stunned. What he unveiled about Neptune, the distant ice giant, challenged long-standing assumptions and suggested that this seemingly quiet member of the planetary family might be far stranger than previously imagined. For decades, Neptune held its place as the eighth planet from the Sun, a cold, bluish orb orbiting in the dim outer reaches of the solar system. Discovered in 1846 not by direct observation, but through mathematical predictions based on irregularities in Uranus's orbit, Neptune's presence was more inferred than seen. Since then, our understanding of it has come in slow trickles, from distant telescope images and a single brief encounter during Voyager 2's 1989 flyby, which offered only a fleeting glimpse into the planet's turbulent atmosphere and violent winds. Despite this, Neptune remained mostly an enigma, defined by gaps in knowledge and an air of mystery that made it both compelling and elusive to planetary scientists. Tyson's announcement cracked open that mystery in dramatic fashion. The centerpiece of his revelation was a series of findings gathered from the James Webb Space Telescope, JWST, and cutting-edge Earth-based interferometric arrays. These instruments had detected patterns and anomalies in Neptune's gravitational behavior, electromagnetic emissions, and thermal output that sharply diverged from traditional planetary models. Tyson explained that Neptune's interior is not the neatly layered structure we once thought, no simple gradient from gas to ice to a solid core. Instead, recent data points to a far more dynamic and volatile environment, one filled with swirling, churning, plasma-like regions and anomalously warm patches buried beneath the cloud tops. These areas defy standard thermodynamic logic, especially for a planet so distant from the Sun and lacking any substantial internal tidal heating from large moons. What's more, these thermal anomalies are not isolated events. Tyson described how these warm patches seem to pulse and shift over time, indicating a dynamic internal process that continues to unfold. It suggests Neptune may have a form of internal convection or even localized fusion-like events, albeit at much smaller scales, generating bursts of heat that travel outward. The mystery of this self-generated heat, far beyond what could be explained by the planet's distance from the Sun, leads scientists to believe there may be internal sources of energy we have yet to fully comprehend. This radically challenges the assumption that only large bodies like stars or massive gas giants can possess internal energy systems of such complexity. Even more startling was Tyson's discussion of Neptune's magnetic field. Already known for being oddly tilted and offset from the planet's center, the new data revealed that the magnetic field is not just skewed but appears to be unstable, shifting and reforming in cyclical patterns that suggest a radically different internal dynamo. Rather than being driven by a metallic core or a deep layer of conductive hydrogen like Jupiter or Saturn, Neptune may be generating its magnetic field through exotic ices undergoing high-pressure chemical transformations. These charged flows could be responsible for the erratic magnetic behavior, hinting at a wholly unique internal mechanism among known planets. Adding yet another layer to this cosmic puzzle, Tyson presented a hypothesis, still in the early stages of scientific consideration, that Neptune might possess stratified cavities or semi-hollow structures within its interior. These cavities could act as resonant chambers for electromagnetic and gravitational energy, radically altering the way the planet behaves under pressure and temperature variations. These proposed resonant structures could also amplify internal seismic activity, potentially creating subsurface quakes or reverberations that generate powerful electromagnetic signatures, something previously considered impossible for a gas giant. If true, this would force a major rethinking of how we classify planetary bodies, not simply by size or orbit, but by their fundamental architectures. It could mean that Neptune, and possibly other ice giants, don't conform to the spherical compression models used since the early 20th century. Instead, these planets might be better understood as composite systems, partially solid, partially fluid, and governed by rules that differ from those applied to either terrestrial or traditional gas giant models. Tyson further deepened the intrigue by highlighting the detection of unusual radio emissions emanating from Neptune, signals that don't match any known natural phenomena associated with atmospheric storms or magnetic field interactions. These emissions, captured at irregular intervals and across a wide spectrum, have a distinct signature, one that oscillates and modulates as if being shaped by internal rhythms. Some researchers speculate that these emissions may be signs of quantum-level behaviors or previously unknown chemical processes occurring under the extreme conditions inside Neptune. Others even whisper about the potential for entirely new states of matter emerging in Neptune's exotic environment, matter that exists only under conditions found deep within ice giants. One of the most compelling aspects of Tyson's presentation was the discussion of superionic ice, a bizarre phase of water where hydrogen ions break free from oxygen atoms, resulting in a strange, electrified fluid that behaves like both a solid and a liquid. Recent evidence suggests that such material might exist in vast layers inside Neptune. These superionic ices could help explain the planet's excess internal heat, its magnetic oddities, and the turbulent activity observed beneath its surface. The behavior of this strange matter, under pressures millions of times greater than Earth's atmosphere, may create a conveyor belt-like motion beneath Neptune's clouds, driving turbulent weather patterns unlike any seen elsewhere in the solar system. These currents of superionic material may be the key to unlocking Neptune's atmospheric chaos. Unlike Earth's relatively stable jet streams or Jupiter's banded weather zones, Neptune's storms appear to erupt suddenly, move at incredible speeds, and then vanish. With wind speeds reaching up to 1,300 miles per hour, faster than the speed of sound on Earth, these violent storms are a signature of Neptune's atmospheric ferocity. Tyson suggested that the storms may not be surface phenomena at all, but rather the visible tip of deeper convective engines, fueled by shifting pockets of heat and strange matter rising from the depths. This radical shift in our understanding has implications far beyond Neptune. Thousands of exoplanets detected by missions like Kepler and TESS are classified as mini-Neptunes or sub-Neptunes, often assumed to be scaled-down versions of what we thought Neptune was. If our home system's Neptune is nothing like we assumed, then neither are these alien worlds. The models used to classify, study, and theorize about their habitability or composition may need to be entirely revised. Tyson warned that we may be applying dangerously flawed templates to distant worlds, mischaracterizing them because of outdated assumptions. He even introduced a highly theoretical idea that left many scientists stunned, that Neptune may occupy a gray area between planet and failed star. Although its mass is far below the threshold for nuclear fusion, its internal energy generation and exotic processes might qualify it for a new class of celestial objects. Tyson likened Neptune to a chaotic system in equilibrium, a body whose balance is not maintained by slow energy decay, like most planets, but by the constant eruption of internal forces, a concept more often associated with stars or brown dwarfs. Perhaps most importantly, Tyson emphasized the role of observational technology. Without the JWST and modern interferometric arrays, these anomalies might have remained hidden beneath Neptune's blue veil. It was a humbling reminder that our understanding of the universe is only as strong as the instruments we use to observe it. As these tools improve, we may find that many of our so-called certainties about planetary science are in fact built on shallow observations and old assumptions. The impact of Tyson's announcement cannot be overstated. It has sparked new lines of inquiry, revived interest in a second mission to Neptune, and reignited debates about the classification of planets. If even one of the 8 planets in our own solar system can surprise us to this extent, what might lie in the dark corners beyond? What secrets are hidden in the Kuiper Belt or among exoplanets that we've barely begun to study? Neptune, once considered the quiet, icy sentinel of the outer solar system, has now emerged as perhaps its most exotic member. Tyson's findings not only deepen the mystery surrounding the planet but also serve as a broader reminder: the cosmos is still full of surprises. In his words, Neptune is not merely a planet, it is a question mark, a challenge, and a window into the deeper complexities of the universe. Tyson's revelation wasn't just about Neptune. It was about confronting the limits of human understanding, embracing scientific humility, and thrilling at the unknown. And with that, our story of Neptune, and perhaps planetary science itself, may never be the same again. As Tyson concluded his talk, The room remained silent, not in confusion, but in awe. The magnitude of the discoveries, the implications for cosmology and planetary classification, and the sheer wonder of uncovering such strangeness in our own celestial backyard weighed heavily on every listener. Conversations afterward buzzed with excitement, doubt, and enthusiasm as astrophysicists from around the world scrambled to re-examine old data and brainstorm new exploratory missions. Neptune has suddenly become not just a subject of intrigue, but a symbol of the unknown, an invitation to the scientific world to explore further, question deeper, and build instruments capable of peeling back the universe's layered mysteries. Tyson reminded us that discovery doesn't always lie in distant galaxies or unseen dimensions. Sometimes, the most profound questions are hidden in plain sight, in the corners of our own solar system that we've taken for granted. With future missions on the drawing board and interest surging in Neptune-focused research, this new chapter may soon transform our entire perspective on planetary evolution, formation, and identity. Tyson's daring to look deeper, and to suggest we may have been wrong all along, could very well be the spark that leads to the next generation of scientific revolution in space exploration.